Hi folks, welcome back to Physics with Captain Rod. I'm making this video here to help you out with numbers 18, 19, and 20 in your homework over magnetism and in AC circuits. So number 18, it says, what is the resistance of a light bulb that uses an average power of 25 watts when connected to a 60 hertz power source having a maximum voltage of 170 volts? So the first thing I'm going to do is write down everything that I was just given in the problem. We were given a power, 25 watts. We were given a 60 hertz source. Talk about what that means in a minute. And a maximum voltage, I'm going to put Vmax here, of 170 volts. Now, this is referred to as the frequency, and it really doesn't have any part in this problem. All it is it's there to let the person know that this is an AC varying voltage source. Right, so we've got a sine wave, one of these guys, varying at 60 hertz, and 170 volts is the peak, the top of the curve. So this is really only here to communicate the fact that this is an AC voltage. So, and again, keep in mind that your numbers might be different than the ones I just read because I set this up to do random. And it says, let's see, what is the resistance of a light bulb? So first I'm going to start with a quick little picture and I'm going to draw a circuit diagram. So this is the symbol for an AC voltage. That takes the place of maybe this symbol for a DC voltage. So we're not going to need a DC voltage source. And then it is hooked to a light bulb. So in a circuit diagram, you would normally draw a resistor to represent the bulb. And again, key concept here, all conducting material here, so this is all one potential up to the light bulb. So very important to realize, red to black is this 170 volts, and over here, red to black, 170 volts. Now, I wrote some equations over here like Ohm's law, V equals IR. When you apply Ohm's law to AC circuits, sometimes people like to write it with little letters, like little v equals little I times R. It still means voltage equals current times resistance. You can always apply Ohm's law whether it's DC or AC. And power is current times voltage, and it's equal to I squared times R as well. Important thing to realize, though, when you're dealing with AC circuits, these need to be RMS values. Your current and your voltage need to be what are called your average currents and average voltages, or your RMS current and voltage. And you calculate your RMS voltage by taking your peak voltage, or your maximum voltage, and dividing by root 2. Now, where the root 2 comes from, that's beyond the scope of the course. If you want to take a look at it, I'm sure I've got other videos on AC circuits where you can find it. But for now, I'm just going to assume this and move on. So we were given a power, and power is equal to I squared times R. Now, I know power, but I don't know an I, and I don't know an R. So I'm going to go ahead and write out the other formula here. Power is current times voltage. Well, we know the power, that's given in the problem, so you can put that value here. We also at least have a way to get the voltage. Now, here's an important part. It says right in the problem, this is a maximum voltage, not an RMS voltage. In these power formulas, these have to be RMS values. So, first calculate your RMS voltage by taking your peak and dividing it by root 2. That value can go here. The power you already have that was given in the problem, that will allow you to calculate the current, and that current will be an RMS current. Then we can do a couple of things. We could either go here and put in our known power and our known current squared and solve that for R. Or you could start with Ohm's law, V equals IR, because the voltage is given, and in the first part I talked about how to get the current, and you can get the resistance that way. Either one will work. Let's see, part B, what is the resistance of a 60 watt bulb? Part B, you do the same way. You're going to do it exactly the same way. You're going to use the same voltage, but a different power. So basically just repeat everything I said for part B using 60 watts here, or whatever it says on your page for the new voltage. And that should be enough to get 18 done. I'm going to call that done and move on. 19, let's see, a certain light bulb is rated at 40 watts. So I'm going to get rid of this stuff. I'll leave those equations there. Alright, so in 19 it says a light bulb is rated at 40 watts, so that's a power. And again, your value may have a different number here. operating at an RMS voltage of 120 volts. So this one is already ready to use. This already is an RMS voltage. What is the peak voltage across the bulb? So what they're asking for in part A is what is the peak or the maximum. So look over here. The RMS voltage is equal to the peak divided by square root of 2. So if you wanted the peak, you would have to multiply both sides by the square root of 2. So just take square root of 2 times 120 and you should get the peak. Part B, what is the resistance of the bulb? So for part B, we know the power, and power can be written current times voltage, or it can be written I squared times R. Now I think we don't have the current, but we do have the voltage. So one thing you can do here is put your RMS voltage here, put your power here, and get the current. Then I'm going to go down to this equation here, put the same power here, and the current you just calculated here, and now you can find R. Oops, not 0, some value. I'll put some number. Right? Now, once you get the current, you could also just go to Ohm's law. Voltage equals current times resistance. And you could put your RMS voltage here and the current you calculated here and get the resistance that way. Either one will work just fine. All right, so that's part B. Part C, does a 100-watt bulb have greater resistance or less than a 40-watt bulb? Now you could go through and do the math, but mainly that's a conceptual question. Remember that as resistance goes up, current will go down. And remember that power is equal to current times voltage. And imagine the voltage staying constant at 120 volts. So that should be enough to conceptually answer that question. If you can't figure it out conceptually, go ahead and just calculate the power at 100, or calculate the resistance at the 100 watts and calculate it again at the 40 watts, and you can figure it out that way. But I think you can answer that conceptually. I'm going to call 19 done. Okay, so there's a figure, and I want to take the time to draw that figure here. So we have an AC voltage, a light bulb. Now in the place of the light bulb, I'm going to put a resistor symbol, because that's what you do in circuit diagrams. And then another light bulb, another resistor symbol, another light bulb, another resistor symbol. And let's see, these are 250 watts lamps. It says 1 and 2, so these are 250 watt, this one, but this one is a different one, 100 watts. Now the way you get different powers is by different resistances, right? Keep that in mind when we work this problem. These two bulbs will have the same resistance, but this one's going to have a different resistance. Now, I'm going to start this by color coding the potentials. I think that's very, very important to conceptually understand why these circuits work the way they do. This is all conducting material, so this is all one potential, right? Go back and look at my video about I facts, and one of the most important I facts is conductors themselves are equipotentials. So because this is all conducting material, this is all at the same potential. Then this is all conducting material, so this would all be at the same potential. Now, anybody watching this might wonder, how do I know this is all conducting material? Well, the answer is, these circuits are made of wires, and the wires would either be copper or aluminum would be the most common, which are conductors. Now notice red to black, and look at red to black, red to black, red to black. See, the potential across all of these are the same. That's the defining characteristic of what's called a parallel circuit, and this is why all the household wiring is all done in parallel. All right, so this voltage here, given in the problem, is 120 volts. That is an RMS value. And the reason I know is I'm sure they're modeling this after a standard household circuit, which is 120 RMS. And it says find the current in each one. Well, if I start with Ohm's law, V equals IR, the 120 is good across every one of these, but we don't know the I or the R, so let's just put this on hold. What we do know are the powers. So power is current times voltage, and power is also equal to I squared times R. Both these formulas are typically important in a problem. So as I look here, I know the power here, 250 watts, so that's a known value. And the voltage is known, red to black, and the red to black is the 120 volts. So this is 120 volts, this is 250. You can get the current that way. Once you have that, you can put that current into this formula and take your 250 watts and put it here and calculate the resistance. Repeat here and here. And I think that'd be done. That's pretty much it for that problem, right? So I think I'm just going to call that good right there. That's how you do problems 18, 19, and 20. Good luck with them. I hope you get them worked out fine. Please call or email if you have any questions. Have a great day.